This is my first conference, so I've never been introduced before. That's pretty rad. Yeah, so my name's Taylor. I just joined the tech workforce in 2020, and this is my first plug fest. I'm excited to be here. Also really nervous, though. Gotta say, as soon as I come up here, I realized that everything I intended to say is just exiting my brain pan. But don't worry, I thought ahead. I brought slides.
Don't worry, that's normal. You'll get over it.
So let's jump right in. So I'm going to talk today about what we're calling enhanced memory protections. I'm going to go over what the current state of UFI security is, and moved into what we're kind of defining as enhanced memory protections, and also different compatibility mode. I'm going to talk about a case study, which is what we deployed with the Surface Laptop 5, and move into some tools and tests that we developed for this. So Michael shared this slide earlier. And basically, again, this is from a presentation by CISA, noting that the firmware vulnerabilities as a percentage of new vulnerabilities out of the NVD is increasing. And unfortunately, this is not because there's a decrease in the number of security vulnerabilities above the stack, but it's also not the case that UFI is getting less secure. Actually, the issue is that a lot of the bootkits that used to be only restricted to state actors are making their ways onto forums to be sold to really motivated hobbyists. Black Lotus is a very notable recent example. And CISA noted that the popularity of UFI, its lack of memory protection enforcements, has attracted exploitation. And as an aside, I just want to note that CISA, when they gave this presentation, immediately after this slide, compared UEFI to unregulated Twinkies, which I got to say is a little blow. So firmware implementations lack a basic memory mitigations that have been present in other system software further up the stack for decades now. UFI implementations vary widely in reliability and security assurance, and because firmware is such a foundational piece of infrastructure, it has these attack vectors can compromise everything above the stack. So, so the summary is that known firmware exploits are not being protected against, and these vulnerabilities are increasing in frequency, and we must do better to harden these harden platforms against these exploits and common memory safety vulnerabilities. So now we'll move into what we're calling enhanced memory protection. I put a slide in here just to make sure that I riff about compatibility as the first point. Obviously, this is going to cause a lot of turbulence in the ecosystem. There are a lot of legacy bootloaders and option ROMs which are not going to be compliant with these sorts of recommendations. And Microsoft is very committed to ensuring that we kind of raise the bar on security in the ecosystem. Hence, they put their best guy on it. That's not true. What I think happened is that they said, oh, hey, this kid can code, but also he's really good at saying sorry. So whenever I break something in the ecosystem, I can just go ahead and say like, oh, hey, I'm so sorry, I didn't mean to do that. And actually act like put me on the firing line when we move other troops upfield. So the first requirement is that we're going to require that the memory attribute protocol be present on every platform. This was out of the UFI spec 2.10. What this does is allows you to get, set, clear memory attributes on ranges. We expect that cores are going to be secured in such a way that when you receive, say, an allocated buffer, it's going to be required that you clear the attributes or change the attributes in the buffer to switch it from being, say, non-executable to being, like if you want to allocate a buffer that you want to put code into and execute, you would allocate that buffer, you would write the code into it, switch from being non-executable to being executable and read-only, and then start executing. The second requirement is that page 0, or the null page, is now going to be marked as EFI memory RP. This is to catch a whole host of common programming errors and old dereferences. Michael mentioned these. But we do know that there are also cases where legacy bootloaders, this null page has been written to on purpose. And so there will be compatibility measures, hopefully, to mitigate those issues. Third is that we would like to implement what we call stack protection, and this is basically just marking the stack memory as EFI memory XP, and then putting at the stack base an RP page so that overflows can be protected against. I didn't note here stack canaries, but that's also something under consideration. 4 and 5, we want to implement image protection, so we're going to require that PE loaders, whenever they load an image, apply XP to data sections and then RO to code sections. This goes in line with the requirements to not merge code and data sections together, and also that we require these to be page granularity aligned, so these protections be applied. And unallocated heap memory, we're going to require that these things are EFI memory RP. This is, obviously we don't want any EFI conventional or unallocated heap space to be used unless it's been deliberately allocated. And so this not only catches, say, overflow, upper overflow issues, but also just issues where people are writing to memory where they shouldn't be. But we want it to be that so no memory range is simultaneously readable, writable, and executable. This, carries with it a lot of consequences. Like I said, when you allocate a buffer, you're going to get that buffer back with some sort of protection attributes. And we're going to hope that you use the memory attribute protocol to remove the protection attributes from that range to do whatever you need with it. But at all times, there's going to be some sort of EFI memory access attribute applied to that range. MMIO ranges, we're going to want these to be in the EFI memory map and then marked as EFI memory XP. An address space which is not present in the EFI memory map, but is part of the overall addressable space, that should cause some sort of CPU fault if accessed. Usually that comes in the form of an EFI memory RP application. I should note that though I think in the ARM spec right now there is no definition for EFI memory RP on ARM platforms, but ART has added CDK2 an implementation of EFI memory RP on ARM by the access flag. So there is a proof of concept out there. So that's all the definitions for how we want to raise the bar for this enhanced memory protection mode. But there are, of course, going to be applications where, or situations where, legacy code cannot be updated. There are binaries which, are causing issues, and there's no way for you to obviously go into that source code and fix the problems. So we're going to also define here a kind of compatibility mode. And the compatibility mode just differs in a few key ways. First, we'll go ahead and make sure that whenever you call core services, the allocated buffers that come back to you, those should be readable, writable, executable, so that you don't have an issue where you get back, say, a non-executable buffer, you write code into it, and then don't use the attribute protocol to update those attributes, and then you end up hitting a page fault. Loaded image buffers will no longer have those restricted access attributes. We won't apply XP to data regions or RO to code regions. And then page 0, because that's pretty commonly used by legacy bootloaders to put data into and read from, we're going to go ahead and unmap page 0. Or I'm sorry, we're going to map page 0 so that doesn't cause an access fault. So Microsoft is working with partners to add support for these enhanced protections. Compatibility mode may continue to be used by legacy bootloaders and OpROMs until the end of their life. And in the future, we want to do a few key things to make sure that we can raise the security bar. We want to push for these enhanced protections to be on by default. We want to make sure we work with our industry partners to produce compatible firmware and develop tools and tests to audit and verify that these protections are in place, and also document how to debug these issues. So, just a few things. As a case study, the Surface Laptop 5 is one of our devices that we shipped. And this is actually shipped with not exactly the definition of enhanced memory protections, but it has shipped with memory protections active for consumers. And we'll walk through a couple of compatibility challenges we encountered with that and how we mitigated them. So just just what this is, it runs a fork of EDK2, is a secure core compliant firmware solution, and has some of these enhanced memory protections active. Some which some don't quite meet the enhanced security bar, but then some are not even present in the enhanced security definition, like say page guards are active. So the first compatibility concern is that unexpected code paths or edge cases could come up, which we did not encounter when testing, which can cause some sort of page fault in the system. And we want to make sure that there's some kind of something we can do to make sure that we don't brick a consumer's device. So because this Surface Laptop 5 is an Intel system, we could use CMOS so that whenever a page fault is hit on a platform, we can go ahead and persist the exception via CMOS, just writing a few bits, saying like, hey, an exception occurred. And then next time when we come around in the boot, we can say, an exception occurred. Oh, maybe we can even make it more granular, say like an exception occurred at this range, at this memory type, and then maybe only disable some sort of protection for that range, or just more broadly, we can disable memory protections. And there are cases where the user of the system can say like, no, I only want to boot with memory protections active. And also disabling memory protections will cause an extra TPM measurement, which can cause you to lose access to some of your secrets. The second compatibility concern is that OpROMs may not be compatible with these enhanced protections. It's been noted that we would like to use the DLL characteristic NXCompat as an indicator whenever we load an image that this image is compatible with these enhanced protections. So if we've loaded a bunch of images and these are all NX compatible, at the point that we get to that we have loaded an image that is not NX compatible, we'll basically go into this compatibility mode so that from then on, the memory protection state will be reduced. And hopefully if you load like an old version of Grub or something, then that will allow the boot to persist. So the exact details of how we're going to reflect to the Windows user that these protections are active, that's all to be determined. We could have a logo test which makes sure that a bunch of these protections are in place. We could also put the same way we do for like core isolation and such in the security window of Windows. We could say hey, you have enhanced memory protections active, and you have a nice little check mark that helps you sleep at night. So we've tried to implement some tools and tests to help us verify that the system is in a secure state and verify that these protections are active. The first one is what we're calling the Memory Protection Test app, and this will go ahead and look at which protections are active on your system, and then try to test those in a few ways. We can either we can say if you have page guards active, we'll go ahead and allocate a page, and we'll try to we'll purposely overwrite the buffer and see if the system resets. And if it does, we'll say okay, that passed. Then we'll move on to the next one. Another way you can do it is you can just go ahead and read directly the page table, and as you can allocate and read the page table and say that hey, are these protections active? If they are, that's another way to pass the test. Or you can use the memory attribute protocol to verify that the system is actually reporting back to you the correct attributes by the protocol. There's also the memory attribute protocol test app, and that tests a bunch of things. It's about some issues that we found when we were actually implementing this on Surface Laptop 5, and then also it just makes sure that that you're giving back the buffers you expect. You're able to clear the access attributes and buffers, things like that. The PECOF image validation, that's been discussed earlier in this talk. It's just a way to check that your images that you load or the images that you test are 4K lined and don't have merged code and data sections and such. And then there's the test for enhanced memory protections, which goes through each of the criteria that is listed, and as best we can test to make sure that they're present. It can check for the presence of the memory attribute protocol. It can go ahead and look through the firmware map to see if all of the effective dimensional memory has the correct attributes, all sorts of stuff. We've actually brought this test with us, so if anybody wants to test a platform that they would like to test, we can run this. Also, what we brought is what we're calling the Dixie paging audit. What this will do is this will collect a bunch of information about it. We'll basically read out the page table and put it into a human readable form and try to match it with, say, GCD types, EFI types. And this gives you a nice human readable format to look at the page table and inspect it, and then also to run some automated tests in HTML to check for some of the requirements. So that's the end of my talk. It's quite short. I'd like to have plenty of time to take questions if there are any. No? Okay.